Everyone, so today we're going to tackle one of the most important tools in all of data science, linear regression. Now it might sound kind of scary, but trust me, the main idea is actually super simple and really, really powerful. Let's dive in.
You know, it all comes down to this one big question that pretty much everyone with data has to ask themselves. You're looking at this mess of data points, right? How in the world do you find a real pattern in there? How do you separate the signal from all the noise?
Okay, so just imagine this is your data. Could be anything, really. Maybe you're tracking house sizes against their selling price, or patient recovery times based on a drug dosage. It just looks like, well, a cloud of dots. Kind of random at first, right? But if you squint a little, you can almost see a pattern, can't you? It looks like it's generally heading up and to the right. The question is, how do we nail that down?
And that brings us to our main topic. What exactly is linear regression? When you boil it all down, it's just about one thing: finding that single, perfect line that best represents the trend in all that data.
And this is what we're aiming for. The whole point of linear regression is to look at all those scattered points and draw one single, straight line that slices right through the middle of them. It's the line that best shows the general trend, the core relationship we're looking for.
So, there you have it. That's the official definition. Linear regression is just an algorithm, a set of rules that finds the line that best fits a bunch of data points. It's like a mathematical way of playing connect the dots, but for dots that don't line up perfectly.
Okay, but why is this so incredibly useful? Well, once you have that line, you've basically built yourself a prediction machine. You can give it a new X value, say the size of a house that's not even on the market yet, and the line will tell you its best guess for the Y value, like its estimated price. This super simple idea is behind tons of real-world predictions.
All right, but that brings up a really important question. I keep saying best fit, but what does that actually mean? Because, as you're about to see, it's all about embracing a little bit of imperfection.
So here's the first thing you absolutely have to get. The line almost never goes through every single data point. I mean, it might not even pass through any of them perfectly. Some of the actual data points are going to be above the line, some are going to be below it. It's just impossible for one straight line to hit every single target.
And these little vertical lines, these gaps, we call that the error. For every single data point, the error is just the distance between where the point actually is and where our fancy line predicted it would be.
Okay, so if every possible line is going to have some error, how does the algorithm pick the best one? This is where the real magic comes in. It's a method called the least squares method.
The algorithm has just one simple job. Its goal is to find the one single line that makes the total of all those little error lines as tiny as possible. It's going to try out tons and tons of different lines, tilting them, shifting them up and down, until it finds the one line where the combined error is at its absolute minimum.
And that's why you'll often hear people call this least squares regression. Now, technically, what it does is minimize the sum of the squared lengths of the error lines. That's just a little math trick to make sure the positive and negative errors don't cancel each other out. But the gut feeling is exactly the same. Find the line that's on average the closest to all the points.
All right, so we've got a good handle on lines in a simple 2D world. But let's be real. Real-world problems are usually way more complicated than that. So what happens when our data gets a little more complex?
So far, we've been using just one input, or feature as we call it, to predict our outcome. And that gives us a nice, simple line. But what if you have two features? Let's say you want to predict a house's price not just by its size, but also by the number of bedrooms. Well, now your prediction isn't a line anymore. It actually becomes a flat plane floating in a 3D space.
And what happens if you have 3 features, or 4, or 100? Well, our human brains can't really picture that. But here's the cool part. The math works exactly the same. The algorithm just creates what's called a hyperplane, which is just a fancy word for a multi-dimensional version of a plane. It still finds the best fit, and the core idea of minimizing all that error stays exactly the same.
So, after all this hard work, minimizing errors, fitting planes and hyperplanes, what's the final result? What does the algorithm actually hand over to us? It's something surprisingly and beautifully simple: a formula.
Yep. At the end of the day, all of that complicated stuff boils down to this one simple formula. You probably remember this one from high school math class, right?
The algorithm gives you the exact equation for that best fit line, creating a perfect little prediction machine just for your data.
So, the whole process is actually pretty straightforward. You start with your data, your X's and Y's. Then, the algorithm's entire job is to figure out the two magic numbers for that best fit line. It finds the perfect A, which is the intercept. That's just where the line starts. And it finds the perfect B, which is the slope or how steep the line is. Once it's got those two numbers, bam, it builds your final formula. It's ready to go.
All right, let's wrap this up with the key takeaways. First, linear regression is all about finding that one best fit line through your data. Second, it works its magic by minimizing the prediction errors using that least squares method. Third, what you get in the end is a super simple formula, y equals a plus bx, that you can use to make predictions. And finally, remember this whole idea scales up, from a simple 2D line all the way to multidimensional planes.
And that leaves us with one last really interesting question to chew on. We've totally nailed straight lines, but what happens when the real pattern in your data isn't a straight line? What if it's a curve? Well, that's a story for another time. Thanks for joining.